Absolute value equals absolute value. What could we possibly do here? Well, we don't need them both to be absolute values. In fact, we get the same answers whether this one's an absolute value and that one is not, or the other way around. This one's an absolute value and that one's not. I'll show you. If we have the absolute value on this one, we don't need the absolute value on this one. Now, we haven't had this yet. We haven't had the absolute value on one side and the other side have a variable in it. But it's not going to change what we do. Either the stuff inside, either the 2x minus 5 equals exactly this x plus 1, or the stuff inside, the 2x minus 5 equals, if this represents one of the things, then the opposite of this, the negative version, if you want to think of it that way. When we had a positive number, we would have the stuff inside as that positive number, or the stuff inside equals the negative version. So that's what we have here. The x plus 1 and the negative of the x plus 1. Now, I'm going to try to stop saying that. I'm going to call this the opposite of x plus 1. And that's because sometimes this will be the negative number and that'll be the positive number. Let's say x was negative 5. If x was negative 5, then x plus 1 would be negative 5 plus 1 would be negative 4. So this side would be the negative, and this would be the one where we would have to take the opposite of the negative number, and it would be the positive one over here. So I don't want to say x plus 1 and negative x plus 1. I'm going to start saying x plus 1 and the opposite of x plus 1, because that is how this is properly read. And thinking about it that way makes a lot of things make sense, as opposed to thinking about it as a negative. From here, we just solve both. So 2x minus 5 equals x plus 1. I can subtract x from both sides. 2x minus x is x. So x minus 5 equals positive 1. I'll come back here. Over here, I have to distribute this negative, and I get negative x minus 1, the opposite of x and the opposite of positive 1. So here I would add x to both sides. 2x plus x is 3x minus 5 equals negative 1. I'm going to go ahead and solve both of these, but I need more room. I'm going to come up here. X minus 5 equals 1, or 3x minus 5 equals negative 1. Add 5 to both sides here. I get x equals 1 plus 5 is 6. Add 5 to both sides here. I get 3x equals -1 plus 5, positive 4. I get x equals 6. Divide both sides by 3 here. X equals 4/3. I need both of those answers. And both of these do check in the original. Now, I said it doesn't matter. One or the other can be the absolute value. Doing it this way, where we had absolute value equals the rest of the stuff, we got a solution set of 4/3 and 6. And you can't see any of that. Let me write that again. We got a solution set of 4/3 and 6 when we had the absolute value on the left. Now let's go ahead. You don't have to do it both ways. This is still me showing you, hey, it really doesn't matter. Let's look at the same problem, but this time, that's an x plus 1. Let's go ahead and leave the absolute values on the right. Well, then the stuff inside x plus 1 is either equal to exactly what's on the other side, or the stuff inside x plus 1 equals the opposite of the other side. The stuff inside equals the positive. The stuff inside equals the negative. And notice, again, I'm writing the opposite of the whole side. Because what happened here? We're going to have to distribute that -5. It becomes -2x plus 5. The negative sign gets distributed. The opposite of 2x is -2x. The opposite of -5 is +5. Since I've already started solving this side, I'm going to go ahead and add 2x to both sides. That gives me 3x plus 1 equals 5. Subtract 1 from both sides. 3x equals 4. Divide both sides by 3. There's the x equals 4/3. Sorry, that's in the corner down there. And this one's shorter. Subtract 2x from both sides. X minus 2x is -1x, or -x. Plus 1 equals -5. Subtract 1 from both sides. The opposite of x is -6, which means x is +6. 6 and 4/3. Same answer we got when we had the absolute value here and the x plus 1 without. So all of that showing you the problem basically twice, just to convince you it doesn't matter which absolute value you drop, but you have to drop one of them. Let's do another like that. I won't show it both ways though. Let's take a look at the absolute value of 3x minus 4 equals the absolute value of 2x plus 1. I'm going to go ahead and leave the absolute value on the left just because, I don't know, I like absolute value equals looking like absolute value equals. But like we just saw, it doesn't matter. So I'm going to drop it on this side, just a plain old 2x plus 1. Now, absolute value equals this. So either the stuff inside the 3x minus 4 equals exactly the 2x plus 1, or the stuff inside the 3x minus 4 equals the opposite of the 2x plus 1. So over here, subtract 2x from both sides. X minus 4 equals 1. Add 4 to both sides. X equals 5. Over here, I'm going to distribute the negative. 3x minus 4 equals negative 2x. Negative 2x minus 1. So I'm going to add 2x to both sides. 5x minus 4 equals negative 1. I'm going to add 4 to both sides. So 5x equals negative 1 plus 4. Positive 3. And if I divide both sides by 5, I'll get x equals 3/5. So my two answers in my solution set, 3/5 and 5. Let's talk about absolute value inequalities. Something that can't ever happen. That's what we started talking about. We said that an absolute value can never be negative. What's another way of saying it can never be negative? Not always positive. That's really close. Always positive or what? If we think of our number line, there's not two choices, positive or negative. There's three choices. You're either negative, you're positive, or you are 0. So we consider all three cases. If we can't be negative, that means we can be positive, but we could also be 0. We can be equal to 0, or we can be greater than 0. Positive things are greater than 0. So this is something that is always true. It is always true that an absolute value is greater than or equal to 0. So when we see this, this is a special case where our answer is going to be all real numbers. What if we had the absolute value less than 0, not or equal to? Well, this one is never true. An absolute value can't be less than 0, because that means that the absolute value would have to be negative. Things less than 0 without the or equal to are negative. An absolute value is never negative. So this is something that would have no solution. What about if it did have the or equal to here? Absolute value less than or equal to 0. Well, remember what this means. This symbol means less than or equal to. We just showed that if it was just less than 0, there would be no solution. So that means, since there's no solution to the less than part of it, we can simplify the absolute value less than or equal to 0 to the absolute value equals 0. And remember what we did when we had the absolute value equals 0. We just dropped the absolute value signs. So the stuff inside without the symbol equals 0 is how we would solve that. Let's actually do one like this. If you're confused what I'm saying there, maybe if we actually have some things. Let's take a look at the absolute value of x minus 5 is less than or equal to 0. Well, less than or equal to, this means the absolute value of x minus 5 is less than 0, or the absolute value of x minus 5 equals 0. An absolute value less than 0, that would be an absolute value negative. That means this has no solution, because an absolute value can never be less than 0. Absolute value of x minus 5 equals 0. Well, that's the same as x minus 5 equals 0, because there's no positive negative version to split this up into. So x equals 5 is our only answer. So the solution set would just be the set with the element 5. Now, to make this be an example of something else that we did, if we had the absolute value of x minus 5 is greater than or equal to 0, well, an absolute value can only ever be greater than or equal to 0. It can't be less than. This would actually be all real numbers, because there's nothing we can plug in that doesn't make it true. If we put a negative number in, a negative number minus 5 is even more negative, but the absolute value is going to be positive, greater than or equal to 0. If we put in a positive number greater than 5, like 6 minus 5 is positive. Absolute value of positive greater than or equal to 0. If we put in a number less than 5, but positive, like 1, 1 minus 5 is negative 4. Negative absolute value becomes positive, greater than or equal to 0. So I did the negatives. I split the positives around 5. What about 5 itself? 5 minus 5 is 0. The absolute value of 0 is 0. 0 is greater than or equal to 0 because of the or equal to. So all real numbers. What if instead of 0 here, I had a negative number? Like negative 4. Well, think it through. All absolute values are greater than or equal to 0. That means since all greater than or equal to 0 things are also greater than or equal to negative 4, it's still all real numbers. Because you know what's greater than or equal to negative 4? 0. And all positive things, those are all greater than or equal to negative 4. Absolute values can only be zeros and positive things. All real numbers in interval notation is negative infinity to infinity because it is all real numbers. It is the whole number line from negative infinity to and through infinity and beyond. Why does infinity get a parenthesis, never a square bracket? Because infinity is an idea. It's not a thing. Since it's not a thing, it can't be equal to that thing. Since it can't be equal, it can't have a square bracket. That's why the infinities are a special case that are just parentheses. It's the idea of forever in the positive direction. Negative infinity is the idea of forever in the negative direction. Okay. Now, we've talked about less than and greater than, less than or equal to, greater than or equal to, in terms of the special cases. Most of the time, absolute value inequalities are not going to be things you can just think through like that. Instead, we are going to have a process that we follow. If we have an absolute value inequality, we're going to treat it just like it's an absolute value equation at first, in the sense that step 1 is always going to be isolate the absolute value. Now you might see some examples that might want to leave the 2 in front or get rid of it by distributing. It's not real distribution. It's properties that we're not going to waste our time going over because we don't need to know them if, when we have something like this, we just go ahead and keep dividing and get the absolute value by itself. It's going to make everything easier in the long run to just keep it all consistent. Isolate the absolute value. Then we're going to have one of two things. We are either going to have absolute value less than, or we are going to have absolute value greater than. So we're either going to have absolute value less than, or we're going to have absolute value greater than. Maybe there'll be or equal to's, maybe there won't be, but we're going to be able to classify it less than or greater than. And then we're going to have a different process for each one. To think about what this process is going to entail, let's break one of these down and dig deep into it. Figure out why it's going to give the things it does, and then we can use the process once we're convinced how and why it works. Let's take a look at, for example, the absolute value of x is less than 3. Okay? On a number line, the absolute value being less than 3 would mean, what is absolute value? Distance from 0. So the distance from 0 is less than 3. So on the positive side, let's shade some things that are a distance from 0 less than 3. I'll give us a 1, a 2, and a 3, like it's a Tootsie Pop commercial. And some negatives, a 1, a 2, a 3. A 3. Okay, here we go. All that stuff, that's like less than 1 away. And now all this stuff is less than 2 away. And all this stuff is less than 3 away. But we don't want to include the 3 because we don't have the or equal to. On the negative side, how much stuff is less than 3 away from 0? Well, this stuff is less than 1 away. And then this stuff is less than 2 away. And then this stuff is less than 3 away. But negative 3 itself, that's a full 3 away. We don't have the or equal to, so we can't put that there. This is all the stuff between negative 3 and 3. This solution could be written as a between inequality. All the stuff between negative 3 and 3. This is really the overlap of 2 lines. It's the overlap of this with that, and that's a parenthesis. Let me make that more obviously a parenthesis. There we go. Same here. Let me make that more obviously a parenthesis. Overlap, that's an intersection. That's an and statement. What are these? Well, this is x greater the -3. And this is x less than +3. The intersection of these two lines is how we get this between. And notice there is the x less than 3. And if we wrote this with x on the other side, swap it all, there's x greater than -3. The big N stays with the x. The point stays with the -3. So that's all a between is. It's an and statement. We can use the fact that this and statement is the answer to this inequality to get a rule for all of these when we have absolute value less than. This means that we drop the absolute value. We drop the absolute value and write it as is. And we drop the absolute value, switch the inequality sign around, so from less than to greater than, and change the positive thing that we have to a negative thing. And we'll get our two answers. In fact, since it's written as an overlap, we could do one better, and we can drop the absolute value sign. We can put another less than in front, and then the negative version of whatever the positive thing is. And then we solve that. In this case, we have the answer. Let's look at a problem, and let's apply our method for absolute value less than. Absolute value of m minus 2 plus 1 is less than 5. Can we use our method yet? No. Why? That's right, because the absolute value is not by itself. We have to subtract 1 from both sides to isolate the absolute value. And we will have the absolute value of m minus 2 by itself with a less than sign. 5 minus 1 is 4. What does our method tell us to do when we have absolute value less than? We're going to rewrite without the absolute value sign. We're going to put another less than, and we're going to put the negative version on the other side. So all that stuff we just did, where I showed you the graph and the overlap and that it's an and statement, that's all well and good. That's where this comes from. That's why this works. So isolate the absolute value, and if it is an absolute value less than, we get a compound inequality. And if we solve this, add 2 to all sides, We're left with m by itself in the center. -4 plus 2 is -2. 4 plus 2 is 6. On a number line, we would have a -2, a 6, no or equal to. So parentheses, and we shade everything inside. In interval notation, this would be -2 to +6. Let's look at another. Let's take a look at the absolute value of x plus 4 minus 3 is less than or equal to 10. What is step 1? Isolate the absolute value. Add 3 to both sides. Why? Well, because then we have absolute value less than or equal to 13. And what do we do when we have less than or equal to? We write it without the absolute value sign. We put another less than or equal to in front, and we put the negative version of what our positive thing is. Solve for x, subtract 4 from all sides. We're left with x in the center. 13 minus 4 is 9. -13 minus 4 is -17. On a number line, we would have -17, we would have +9. Square brackets because of the or equal to, and our x is everything in between. We shade inside. In interval notation, we'd have the interval from -17 to +9. Let's explore greater than. If you need a break, take a break. We've still got another 30-some minutes left. And we're exploring greater than. So let's take a look at, we'll do it the same way. The absolute value of x is greater than 2. If you have a sneaking suspicion that this number line is going to look like the everything else of if this was less than, we know if this was less than 2, we'd end up everything between 2 and -2. If you're thinking this is going to be the rest of it, you are right. So 0, 1, 2, 3, 4, and so on. -1, -2, -3, -4, and so on. Remember, absolute value means distance from 0. So we would be shading things where the distance from 0, the absolute value, is more than 2. So here, the distance from 0 is less than 1. It's less than 2. But here the distance starts being greater than, but 2 itself, the distance would be equal to 2, and that doesn't work. So we'd use a parenthesis, and then this stuff is greater than 2, greater than 3, greater than 4, but that still just means it's all greater than 2. Over on this side, distance from 0 is less than 2. And then here, the distance from 0 would be 2. We can't use that. So parenthesis. But everywhere out here, the distance from 0 is greater than 2. So this is two separate intervals joined together as one answer. What does it mean when we bring those in? That's an or statement. This is a union. This interval 2 to infinity is the same as x greater than 2. This interval, negative infinity to negative 2, that's x less than negative 2. And it's an or statement. An or statement because or is union. And we're taking these two intervals and we are joining them together and saying that both of them together make up the graph of where the absolute value is greater than 2. So it is the wing stuff. And let's find out what our shortcut is by looking at this. Well, this one, we can just drop the absolute value sign. X greater than 2. That gives us that one. And then we say or. And we're going to, it looks like, drop the absolute value, switch the sign, and change the positive to negative. That's the same thing we did for the less than. But this one we can't write as one thing. It's not an and statement. It's not an overlap. This has to be written as two separate ones. Change greater than to less than, change positive to negative, and that'll give us the other one. Now, what do I mean I can't write this as one thing? Well, if we were to try to join them together so that the negative 2 was over here, the negative 2 would have to have the greater than sign. The x would have the little point, and then we'd have greater than 2. Remember, we can't write it this way. This means greater than. There isn't anything that is both less than a negative number, but also greater than a positive number. That's why we can't write it like this. This sort of thing can only be for and statements. This is what we would write for the absolute value of x is less than 2. For greater than, two separate things with an or statement. Drop the absolute value, that's our first. Drop the absolute value, switch the sign, and switch positive to negative. That's the second. Practice time. The absolute value of m minus 2 plus 1 is greater than or equal to 5. Step 1, isolate the absolute value, get it by itself. And then we make our decision what to do. Absolute value of m minus 2 is going to be greater than or equal to positive 4. Absolute value greater than, split it into two things. And it's an or statement. First one, we just drop the absolute value. So m minus 2 is greater than or equal to 4. The other one, drop the absolute value, m minus 2. Switch greater than or equal to less than or equal to. Change positive 4 to negative 4. And that's how we make sure we get the wings. Add 2 to both sides. M greater than or equal to 6. Or add 2 to both sides. M is less than or equal to negative 2. How do we graph this? On a number line, we have less than or equal to negative 2. We have a 6, and we are greater than or equal to that. In interval notation, negative infinity to negative 2, square bracket, because of that or equal to. Square bracket at 6 to infinity. Remember, parentheses with the infinity, even though we have the or equal to, even though we have the square brackets here, because they are always parentheses for negative and positive infinity. And how do we connect these? With a union symbol. So that is the interval notation form of the answer. Let's look at another one. Let's come to our absolute value of x plus 4 minus 3. This time we'll have it greater than 10. Last time we did one like this, it was less than or equal to. I can start doing the steps a little faster because we know they're the same. Isolate that absolute value first. Absolute value of x plus 4 is greater than 13. Absolute value greater than, two things, or statement. Drop the absolute value. Leave the rest alone. And then drop the absolute value, switch it to less than, switch it to negative 13. Subtract 4 from both sides. X is greater than 9. Subtract 4 from both sides. X is less than negative 17. These are the same things we got when we did it with the less than. But when we did it with the less than, we ended up graphing the middle stuff. Here we have our negative 17 and we have our 9. And we are greater than the 9. We are less than the negative 17. So negative infinity to negative 17, union 9 to infinity. And that's going to be our answer there. Okay. Let's kind of build all of this stuff together now. Let's overcomplicate and let's see what happens. Okay, 2 times the absolute value of 6 minus m minus 3 is less than 7. So we want to get the absolute value by itself. Pretend for a moment, this is not the problem, but pretend for a moment we had 2x minus 3 is less than 7. What would we do? We would add 3 to both sides. 2x is less than 10. We would divide both sides by 2. X is less than 5. We do the same things while we're trying to isolate the absolute value. The same things. It's just like solving for the absolute value. So we want to get the absolute value by itself. We've got to get the term with the absolute value in it by itself. Undo minus 3 with plus 3. We're left with 2 times 6 minus m. Next, divide both sides by 2. We get the absolute value of 6 minus m, not 16 minus m, is less than 5. Just like the x version had x is less than 5 because we did the same things. We added 3 to both sides. We divided both sides by 2. We wound up with this. And I'm going to move it up here so that we have room to work on this and finish this problem. We had to get it all the way to the absolute value being by itself on one side. And from there, what do we see? Absolute value less than. So what do? We drop the absolute value. We put another less than in front, and we put the negative version of our positive number from the right on the left, and then we keep going. So far, so good. Here, to get the m by itself, we need to get the minus m by itself, which means we need to get rid of a term that's a positive 6, that's a plus 6. So we subtract. We wouldn't divide because it's not multiplied. We're not getting rid of multiplying. We're also not doing the opposite of subtraction because this is a positive 6 minus m. The minus stays with the m. So we want to get rid of the 6. We do that with minus 6. So 6 minus 6 goes away. We're just left with minus m in the center. Whatever we do in the middle, the minusing of 6, we must do on all sides. Negative 5 minus 6 is negative 11. 5 minus 6 is negative 1. We don't want to solve for minus m, though. We want to solve for m. So we can't just go and change all the negatives to positives and just leave everything else alone. Here, this is still a line that makes sense. Negative 11 is less than something, which is less than negative 1. If we thought about the number line here, again, this is not the answer. I'm just taking a moment to talk about where we are in our work. So if we were thinking about a negative 11 and a negative 1, negative m must be somewhere in here, in between here. The opposite of our answer must be in there somewhere. If the opposite of our answer is over here, where's our actual answer going to be at? Well, the opposite of negative 1 is 1, and the opposite of negative 11 is positive 11. So if the opposite's in here somewhere, the real answer must be over here somewhere. So I'm betting, just based on looking this through, and I'm not using algebra, I'm just looking at the graph and talking about what this means. I'm betting that the answer is going to be this. Oops. Between 1 and 11. So I just realized I cut off here. This is just an 11 with a parenthesis right down here. So 1 and 11. So I can't just change this to positive 11 and this to positive 1 and this to m and leave it less than, because this wouldn't make any sense. This would have to be less than this to use less thans there. But how do we go from a negative to a positive like this? We're dividing both sides by negative 1 or multiplying both sides by negative 1. And what do we do when we multiply or divide both sides by a negative? We would change less than to greater than. And remember, when we write something like this together, we don't want to use the greater thans. We want it in the other form. So if we switch the whole thing around, we have a 1, and then the 1 has a point, and the big N goes towards the M. And then the M has a point, and the big N goes to the 11. And oh, would you look at that? That's the interval from 1 to 11 that we reasoned would be the answer. On a number line, there's 1, there's 11. The answer is the stuff in between. Three times the absolute value of 5 minus x plus 2 is less than or equal to 14. Go ahead and get started on isolating the absolute value. So hopefully you've been able to subtract 2 from both sides. That gives us 3 times the absolute value of 5 minus x on the left. And then divide both sides by 3. Do not distribute the 3. Divide both sides by 3. You want to get this by itself by making it simpler. Doesn't actually change anything if you try to distribute. It's not even real distribution. It's that weird dome stuff. It's not always going to work. You never know what to expect. The absolute value of 5 minus x is going to be less than or equal to 4. Let's continue to solve this. Still about 15 minutes left. It's an absolute value less than, just like we just did. So we drop the absolute value. We put another less than or equal. Put the negative version of our positive number. Subtract 5 from all of the sides. Negative x in the center, the opposite of x in the center. 4 minus 5 is negative 1. Negative 4 minus 5 is negative 9. This is still making sense at this point. Less thans, we have the least on this side, we have the most on this side. Same order as the number line, basically. Divide all things by negative 1 is going to change minuses to pluses. But it's also, since we're dividing by a negative, going to switch less thans to greater thans. Negative 1 divided by negative 1 is positive 1. When we write it together like this, we got to switch it all around so that they're less thans, but it still needs to be the same. So let's move this 1 all the way to the left, and then we have the point with the 1, the big end towards the x, and then the point with the x and the big end towards the 9 on a number line between 1 and 9. We would have square brackets, and we would be all the stuff in the center. Interval between 1 and 9. Square brackets because of the or equal to. Let's take a look at negative 2 times the absolute value of 3x plus 1 is less than or equal to negative 4. Now, at first, you might look at this and think it's one of those special ones. It's not, though. And you're going, wait a minute. I was barely following you at the beginning of this, but you said that an absolute value can never be negative. So it can't be less than or equal to a negative, right? This isn't in the final form. So this is why I'm warning, always put it in the absolute value by itself form first, because look at what happens. To get the absolute value by itself, we have to divide both sides by negative 2. Dividing both sides by a negative is going to change less than or equal to greater than or equal to. We're just going to have the absolute value of 3x plus 1 on one side. On the other side, negative divided by negative is positive. So -4 divided by -2 is +2. So here we have absolute value greater than or equal to +2. When it's absolute value greater than, we split it into two things. With an or statement, one, we just drop the absolute value sign and keep everything as is. 3x plus 1 greater than or equal to 2. Or the other one, we drop the absolute value, we change greater than to less than, or equal to in this case, and we change +2 to -2. If I subtract 1, I get 3x is greater than or equal to 1. If I divide both sides by 3, I get x is greater than or equal to 1/3. Or the other side, subtract 1 from everything, I get 3x is less than or equal to -3. If I divide both sides by 3, I get x is less than or equal to -1. Don't switch the sign just because this is a negative. We're dividing by a positive. It's only when we divide by a negative. Negative divided by positive doesn't change the sign. So let's write our answers. I'm out of room, so I'm just going to move this up. X greater than or equal to 1/3, or x is less than or equal to -1. On a number line, that's a greater than or equal to. Just moving it down out of the light spot. On a number line, we would have -1, and then we would have +1/3. We would have square brackets for our equal to, and we're greater than 1/3 or equal to, and we are less than or equal to -1. So -infinity to -1, union 1/3 to infinity.